This is Lecture 2 of Module 5 from the book Problem Solving Guide for Mechanics and Thermodynamics. The topic, work and kinetic energy. The past two modules we worked on F equals ma. Module 3 was linear acceleration. Module 4 was circular motion. Here we're going to look at the energy given to an object by the forces acting on it. We're going to start with a very simple situation, a 1 kilogram block and a 2 kilogram block at rest on a frictionless horizontal surface acted on by a 10 Newton horizontal force over a distance of 10 meters. We're going to pull on these two blocks for 10 meters with a 10 Newton force. We're going to calculate the final speed of each using kinematics. From F equals ma, we can determine the acceleration of the 1 kilogram mass is 10 meters per second squared, and the acceleration of the 2 kilogram mass is half as great, 5 meters per second squared. From the equation v final squared equals v initial squared plus 2ax, setting the initial speed equal to 0, the acceleration equal to 5 meters per second squared, we can get the final speed of the 2 kilogram mass. It's 10 meters per second. Now let's look at the 1 kilogram mass. Its acceleration is twice as great. Its initial speed is also 0. The distance over which the force acts is 10 meters. And we get the final speed of 14.4 meters per second. We might have expected 20 meters per second, but that is not the case. It's not twice as fast. Let's use the equation v final squared equals v initial squared plus 2ax to see what happens when a net force acts on a mass over a distance x. We're going to solve this equation for the term ax, subtracting v initial squared from both sides, dividing by 2. And we're going to put an m on both sides because we want ma, because ma is the net force. So we're multiplying through by m. On the left-hand side, we now have ma, and that's F net. On the right-hand side, we can multiply through by m and separate the terms, put the 1/2 in each term, and we get F net x equals 1/2 mv final squared minus 1/2 mv initial squared. The 1/2 mv squared, that's the kinetic energy. So the right-hand side is the change in kinetic energy. The left-hand side, F net times the distance, that's the work done on the object. And x, it has to be the distance moved in the direction of the force, because that's how we calculated the final speed, the force in the direction of the displacement. The term on the left-hand side is the work done on the mass. The two terms on the right-hand side are the final and initial kinetic energy, respectively. This is the work-energy theorem. From this relationship, we can see that it takes 4 times as much work to double the speed of a mass. And now we can show this explicitly. So with the 2 kilogram mass is moving at 10 meters per second when the 10 Newton force acts on it over a distance of 10 meters. Now we're going to pull on it until it gets to 20 meters per second. We want it to go twice as fast. We're going to calculate that distance. So now the final speed's known. It's 20 meters per second. Same equation, v final squared equals v initial squared plus 2ax. The acceleration is the same. The force is the same. What distance do we have to pull on it to get it up to 20 meters per second? Substituting in the numbers, we get 40 meters, which is 4 times bigger than 20 meters. After 10 meters, it's going 10 meters per second. After 40 meters, it's going 20 meters per second. The energy an object has is a function of the square of its speed. The kinetic energy is 1/2 mv squared. So if there's a storm, a windy storm, wind speeds of 100 miles an hour are 4 times worse, 4 times energetic, everything else equal, than a wind speed of 50. A 20-gram rifle bullet moving at 4,000 feet per second will do 4 times as much damage as a 20-gram rifle bullet moving at 2,000 feet per second. With the same braking force, a car moving at 80 miles an hour needs 4 times the distance to stop than a car moving at 40 miles an hour. And it's easy to see this relationship when looking at the average speed. The distance equals average speed times time. It's an equation you knew before you took this course. X equals v average t. The car going from 80 to 0 will take twice as long to stop as the car going 40 to 0, so the time is twice as great. And the average speed, 80 to 0, is twice as great as the average speed from 40 to 0. So we have twice the time to stop, twice the average speed. Stopping distance is 4 times as great. Example problem 6 on pages 23 and 24, the texts show this clearly. So to effectively solve problems using the work energy theorem, we should really multiply out the left-hand side, which is F net x. F net is usually the sum of more than one force. So this is what we're going to do. F net x, we're going to separate that left-hand side into the dot products, F1 x1, F2 x3, F2 x2, F3 x3, etc., depending on how many forces are on the object. Here we have three forces. We have the 10 Newton force that's pulling on it horizontally, that's accelerating it. Gravity's not doing anything. Gravity's straight down, the mass is moving to the right. The normal force is straight up. It's not increasing or decreasing the kinetic energy of the block. It's not contributing. Only the 10 Newton force is contributing. So the dot product is 0 for the normal force and the gravitational force. The movement of the block is only in the direction of the applied force, so the work done by gravity is 0. It doesn't move in that direction. The work done by the normal force is 0. It doesn't move in the direction of the normal force. So these distances that go with the forces are the distances moved in the direction of the force. And it should make sense that gravity doesn't speed up the object if it's moving horizontally. So I think we're ready to solve some problems. 80-kilogram bungee jumper jumps from a tower that's 60 meters above the surface of a river. The bungee cord is 40 meters long. Stops the jumper, jumps just at the surface of the river after falling 60 meters. We're going to treat the jumper as a point mass, not worrying that he's tumbling or whatever. And we're going to calculate the stiffness of the bungee cord. What is the speed of the jumper after he is falling a total distance of 50 meters? So now he's still moving. And then part C, what is the acceleration of the jumper after he has fallen a total distance of 50 meters? So let's use a neat, good, well-labeled diagram. There's the bungee jumper. That's the relaxed length of the cord, 40 meters. There's the stretch. That's x. So that's the bottom of the trajectory. His speed is instantaneously 0. So let's put v equals 0 in the diagram. Gravity did work on him to increase its kinetic energy. He's moving in the direction of the gravitational force. That's positive work. The bungee cord pulled up on him and he's moving downwards, so it's going to decrease his kinetic energy. Another way to say this is the bungee cord did negative work on the jumper. Let's start with the work done by the gravitational force. The force is constant. It's mg. mg delta y is the work done by gravity. So the force is 800 newtons. The distance is 60 meters. The work is 48,000 joules. The work done by the cord, we stick a negative sign because the force is against the motion. And we get 1/2 kx squared. X is 20 meters. That's the stretch. Don't put in 60 meters in for x. So we need to determine the work the cord done on the guy. And it must be minus 48,000 joules because he stopped. He started at rest. He ended up at rest. His change in kinetic energy is 0. The total work done on him must be 0. So the work done by the cord must be minus 48,000 joules. And we can set that equal to minus 1/2 kx squared, and we can solve for k. It's 240 newtons every meter. That's the answer to part A. Part B, we're going to have a different snapshot, right? 50-meter fall. And let's draw that picture so we can see what's going on. Now x is only 10 meters, and he's moving now. The net work, total work is not 0. Gravity does positive work on the jumper. The cord does negative work. Total work would not be 0. The work done by gravity on the jumper is mg delta y, and it's positive. It's 40,000 joules only. The work done on the jumper by the cord, 1/2 kx squared negative, that took away 12,000 joules. So gravity made a deposit of 40,000 joules into kinetic energy of the guy. The cord made a withdrawal of 12,000 joules. The net is plus 28,000 joules, and that is the change in kinetic energy. He started at rest, so it's just 1/2 mv final. The initial is 0. So we can solve for his speed, and we get 26 meters per second, which is close to 60 miles an hour. Now we can do part C to get the acceleration. We have to draw You get forces. F equals ma. The force of gravity is 800 newtons downward. It's 800 newtons downward during the entire fall. It's his weight. Now we have to get the force the cord exerts, and that's changing because it's being stretched. So F gravity is 800 newtons. We'll put that in the diagram. Now for the cord, F equals kx, and that's upward. We don't need the negative sign to tell us it's upward. So let's put that in the diagram. That's 2400, that's 800. The net force is 1600 upward, and this is ma. His mass is 80 kilograms. We can plug that in, and we can solve for a, and we get 20 meters per second every second upwards. 2 g's upward is the acceleration of the guy. The work energy theorem states that the total work done by all the forces on an object is the change in kinetic energy. And you know, it's useful. But we can completely replace it with the fundamental principle of physics, the conservation of energy. So instead of summing the work done and worry about the distance moved in the direction of the force, we can say, look, the total energy in a closed system is constant. One of the forms energy takes is kinetic. Things are moving, 1/2 mv squared. But there's other forms. In a closed system, energy goes from one form to the other, but the total is constant. And that's the principle of conservation of energy. It's more intuitive than the work energy theorem. In lecture 3 for this module, we're going to be transitioning from the work energy theorem to the fundamental principle of the conservation of energy.